Rise and shine, Explorer. Our oxygen levels are steady, and our battery is replenishing nicely. That's cause for a small sigh of relief, wouldn't you say? But let's not lose sight of the task at hand. We have another glorious day of repairs to conduct. Today, we're going to shift gears and delve into a bit of digital logic. We'll be learning about bits, data types, and why choosing the right one for your variables can make all the difference. Efficient memory usage is essential for our system to function optimally, especially on low memory devices like our Hero board. Moreover, we're going to expand the depths of our coding efforts. We'll work on a piece of code whose intention is to calculate our ship's battery percentage. Not only will this give us a clearer idea of our power situation, but it will also be a practical application of the concepts we're learning. Ready to get your hands dirty with some binary? Of course you are! Let's get to it! Well, well, aren't you lucky, Explorer? Today you get to enjoy a bit of a hardware holiday. How delightful for you. We're leaving the wires and boards be. They've had quite enough of your expertise for the time being. Before you start daydreaming about a leisurely day off, let me assure you we're not on vacation. There is still much work to be done. While the hardware is blessedly out of harm's way for a day, we're going to fill the void with a thrilling, deep dive into the captivating world of coding. Yes, that's right. More mesmerizing mazes of bits, bytes, variables, and functions are waiting for your full attention. This isn't just about expanding your tiny knowledge base for the sake of it, you know. We're doing this so we can craft more refined, more efficient code. In layman's terms, smoother operations and quicker fixes lead us to a faster escape from this underwater blunder that we're in. So buckle up, Explorer. It's high time you familiarize yourself with the finer points of our Hero board's language. We've got some serious coding to do. Ah, joy! It seems you're thirsty for knowledge, Explorer. We'll hold on to your seat. I'm about to drop some wisdom bombs on you. First, there's this delightful little thing called a bit, the smallest unit of data there is. It's binary, which in this case means it's either 0 or 1. Its simplicity is quite adorable, isn't it? Combine 3 of these and boom, you have 8 unique integer numbers. Mathemagic. Next, let's graduate to the integer. It's a little bit chunkier, with a typical size of 16 bits. This gives you a marvelous range of about plus or minus 32,768. Not too shabby, wouldn't you agree? When it comes to integers, we're not bound by one path to stroll down. We've got 2, signed and unsigned. The signed integers take more of a straightforward path and have a bit that acts like a flag for whether the number is positive or negative. Unsigned integers, on the other hand, don't bother with this. As free spirits, they take the scenic route, living their life positively all the way, hence the bigger range of numbers. Now, take our photoresistor. It's a modest creature, outputting a value between 0 and 1023. It's just 10 bits worth of data because 2 to the power of 10 equals 1024. So, an integer is more than adequate to store it. But don't get too comfortable. Our battery capacity variable is set at a lofty 50,000, which outclasses the standard short integer maximum of 32,768. Thus, it needs the VIP treatment, which defines it as an unsigned integer. Next up, meet float. This one likes to live a bit on the edge, handling decimal numbers with precision. Imagine 123.4567. It has a precision of 7. Not bad, huh? Then there's double. It's a float that hit the gym and got buff. It's 64 bits of power capable of holding values up to a mind-boggling 10 to the power of 308. Veering off from variables, let's shine some light on void. It's what we use when we're defining functions that don't give anything back. We'll dive deeper into creating our own functions soon enough. So there you have it, a crash course in basic digital logic. Its overwhelming nature is similar to drinking from a fire hose. I know, but fret not. We'll be practicing these concepts soon enough. Shall we push on, then? Today's mission involves writing additional logic in order to print the battery percentage to our handy serial monitor that we discussed yesterday. Of course, we don't want to spend time rewriting the print statements all over the place in our code. Instead, we can create a new function. We can start with the word void. This is what the function will be returning. As you may have guessed, void means that it will return nothing. This also means that we don't need a return statement, since the compiler deems it unnecessary. I recommend you name it something relative, such as print battery percentage. The parentheses can be empty since we have no parameters we need to pass into the function. Finally, everything inside the brackets is what will execute when you call the function. When the second closing bracket is reached, it will return to where it was called from in the code. If my assumption is correct, it is likely setup or loop. In the end, your newly created function might look something like this. For the line by line, let's jump to the information cached on your computer. I've also added this to your mission resources for future reference. I'll be waiting patiently for your return.
Hello everybody and welcome back to day 7 of repairing your spaceship battery. Yesterday we were successfully able to blink the LED either very fast or very slow depending on how much light we decided to put on to the photoresistor during the simulation. And today we're going to be taking the next step to fixing your battery, and we're going to be adding in a way to print the percentage of the battery that you guys actually have left to the serial monitor so you guys can actually take a look and see how desperate of a situation you're actually in. So to get started, I did leave the wiring the exact same as yesterday. Nothing has changed from that above, as you can see, but same thing, photoresistor going into A0. We have the 5-volt line going in here, and we absolutely do need to complete the circuit. So completed the circuit here into ground. And so without further ado, we can get into the new code for today. So the code I have over here on the right, you'll notice this is basically where we left off yesterday. So I'm just going to ignore the serial monitor down there, and I'm actually going to go in here and I'm going to, well, first of all, I'm basically going to delete most of this. To be honest, I'm just going to start from scratch. The only thing I'm going to keep is this define up top, and the rest of it I'm just going to redo. Boop. And with that, we have a nice, clean, fresh slate. Starting at the very top, the only thing I didn't remove, because I felt like it would be useful for today, is the photoresistor pin A0. Again, we need to have our pin defined somewhere, and for the pin we'll be using, and that is going to be analog 0 for our photoresistor pin. The only thing I cut from yesterday. After the photoresistor pin A0 is defined, we then need to define just some arbitrary value for what we should put for our battery capacity. And this is going to be used later in the code. I'm going to use pound define, and I'm going to say the battery underscore capacity, and I'm going to set it to an arbitrary value of 50,000. It doesn't really matter necessarily what it is, but I'm just going to set it to 50,000. What is 50,000? That is 50,000 battery capacity units. Again, this is for simulation purposes, so the number isn't really that important, but make it something big. It's going to make it easier later on. I'm going to use 50,000. Going into setup, we're going to set up our pins, defining what they're used for. So we can say pin mode, and this is the same as last time. Technically, I didn't have to delete this, but we're setting the photoresistor pin as what? An input. Remember, inputs or outputs. This is an input. It's going in. It's being we're going to read the value on the board to see what it's actually giving us. It is inputting into the board. Next, we're going to go to the serial.begin. This basically just tells us, hey, we do want to actually use the serial debugging this time on execution, and this only needs to be set up once. Same thing as last time. I'm going to be using baud rate of 9600. You can use a different baud rate if you wanted to, but just know that you do have to, generally you have to select which one it is if you're using the Arduino IDE, but since this is the Tinkercad IDE, you can actually, it might automatically select what it's supposed to be using. So, but 9600 is a very typical baud rate that's used for debugging. After that, we can go into our loop. So, first we need to know what our initial battery level even is going to be. So, for simulation purposes, again, because it's a simulation, Let's pretend that our battery level is completely empty. Let's say first time we go through, it's dead. It's completely zero. It's zero. Let's start with that. We can say unsigned int battery level equals 0. Now, why did I say unsigned integer? Again, because it would be weird for the battery to go negative. That doesn't make a whole lot of sense. So unsigned is going to keep it anything 0 or above. Now we have the following. We have inside of here void loop. Actually, little mistake here. This unsigned int battery level, because every time we go through the loop, it's going to override it and set it to 0. If it's inside loop, that should technically be outside of loop, because otherwise it would just override it every single time we went through back to 0. And we don't necessarily want it to do that. That value should hopefully eventually change now that we have our solar panels set up in place, and hopefully charging should start to work. So inside of loop, we can have a little bit of logic here. So for example, obviously if the battery is not fully charged, then, well, we want to start charging the battery. Otherwise, if it is fully charged, then we would probably want to stop charging the battery because we don't want it to go over 100%. That would probably destroy our battery. So let's add in a little bit of logic here. If the battery underscore level is less than battery capacity, which is this arbitrary value we stated up here at the top, basically saying if it's not fully charged, then what do we want to do? We want to charge it. So we can charge it by saying the battery level is equal to the battery level. Oops, this should be an underscore. Plus analog read the photoresistor pin. Now what is this doing? This is essentially taking whatever the value is that it reads on the pin. So remember how solar panels work. If they get a little bit of light, you're going to get a little bit of charge. But if you get a lot of light, full direct sunlight, you're going to get a lot more charge because, well, there's more sun, more charge that it's able to be getting back into the battery. So this is essentially saying that we're going to take the battery level and we're going to set it to whatever the battery level was plus whatever it reads on the photoresistor pin. So if it's very bright, it's going to be adding quite a bit. And if it's dim-ish, it's going to be adding a little. But essentially, this is going to show the battery level going up to 100, hopefully over enough time. Even if it's dim, it'll just take longer to charge. Next, we go down and we want to have a little bit of additional logic here. So if the battery underscore level is somehow adds up to be greater than the battery capacity, basically, did we accidentally, for example, make it too big to where it went over 100% in that line above? Did it accidentally go above 100% right then and there? If it did, well, then we need to have this if statement here that basically says, hey, we can't go over 100%, so let's just set it back down to whatever the capacity was because we don't want it to go over 100. Then, after that, we can actually just end our if statement here. So this bracket will go here, and then this bracket's for this here. So this is one if statement, this is the outer if statement. Whew. And once we're done with that, I want to print the percentage. I actually just want to see what it is. I want to debug it. So what I could do is I could say serial.println in here, and I could, print whatever the battery level and what, etc. Or I could make a new function that will either print if it's what the percentage is or fully charged, depending on a little bit of conditional logic. And instead of writing that logic right here, I can actually just make a function and I can call it. So we have two functions in this program. We have setup and we have loop. And those are built-in functions that the Arduino IDE, or Tinkercad in this case, will automatically give us, and they're required by default. But we can add as many as we want. We're not limited to just these functions. We can make our own. That's something that's done all the time. So that's what we're going to do. We're going to make our own function. And what we write to do this, Astrid has already explained all of this, but as just a little quick recap, the first thing we have to write is what it's going to return. In this case, we're writing void. It's not returning anything. There's nothing to return here. You can write int if it's supposed to return an int. We can write double if it's supposed to return a double. We can return whatever it's going to end up returning, you put here. But since this isn't going to have to return anything, it's just executing a block of code that I don't want to have to copy and paste it over and over again. I just want to be able to call this code and it's just going to execute it. I can just say, hey, this is void print battery charge level. And then I have the parentheses, open parentheses, close parentheses. And normally, if you had parameters you needed to pass through to this function, you'd put them in here, but there are none. So you can just ignore it and keep them empty because there's nothing to pass through. And now we have a function void print battery levels. So in here, I want to add in a little bit of conditional logic. So actually, real quick, this is where I'm going to call it. So I can call this function that's not yet complete by going like that. And it'll quite literally, at this point here, jump to this function, execute it, and then jump back and start executing straight from the line right after. So if it goes here, it's going to immediately jump and execute this line, this line, this line, this line, whatever I end up putting in here. So now, without further ado, let's actually finish this function up. Now, if it's not 100% completed with the charge, then I want to print that. I want to print what the percentage is. And if it is done, well, I want to say it's fully charged. I want to print fully charged. So that's how this logic is going to work. How do we do that? Well, if it's not fully charged, if the battery level, underscore level, is less than the battery capacity, then it must not be fully charged. So that would be our first condition statement. Then we can say serial dot print ln, or I guess serial dot print. Oh, let's see. Let's display it as a percentage. Now, to do this, I'm going to actually cast a data type onto this. So I'm going to convert whatever battery level is to a double. And so I'm doing this because I want to be able to, when I divide it, I want to be able to say that this is going to be a double, and then this battery capacity is also going to be it needs to be a double. And I do this because I want to be able to get a percentage, a very exact percentage with a decimal point. Integers won't give me that decimal point, but by casting them to doubles, both of them, and then doing the division, I should be able to get a nice decimal point at the end of it. So I can go that, and then I want to multiply by 100 because it is a percentage at the end of it. And this will display a charge percentage to our serial monitor. Next, I can go new line, and I can go serial print ln, and I can just say I want it to be the percentage sign. And let's actually just real quick make this a capital. And with that, this should now display what our battery is as a percent. But there's also the other case. That case would be, let's just say it's fully charged. If the battery level is not less than the battery capacity, meaning that it's either equal to or it's greater than, but there really should never be a case where it's greater than, I hope not. realistically it would have to be equal to. Then we can say else serial dot print ln, and this is the only other case it could be, hopefully, if our battery's really broken. Then I want to say fully charged. Maybe even add a little smiley face in there. And then, without further ado, should be the end of our logic for our code. So let me actually clear this output here for the serial monitor, and let me start the simulation. So if I go here, oh, I guess I found a little error. So now, without further ado, let me go up here, and as you can see, the charge level is increasing, and I can actually change the rate at which it does. Boop, fully charged really quick. And without further ado, you can now see, in simulation purposes at least, yours is not yet completed with the fully charged, unfortunately. But for simulation purposes, this is now fully charged, meaning that all the battery's full. In a real life scenario, this obviously wouldn't happen that quickly. I just wanted to show for simulations that it does go, you can see progress, but in your case, it would probably take a lot longer. I'm talking maybe a few hours at the very least once you deploy your solar panels up above the water sea level. But that will be the next step after this. The code is working, the simulation is working. Now all that's left is for you to take these steps and go execute them on your ship and take that step to actually get your battery fixed. Without further ado, I look forward to hopefully in the next couple of days seeing a fixed battery on your ship. Almost there. See you then.